This video is the first in a series for linear algebra and applications. I like to start all my videos with an overview slide that covers the main points of the entire video, and generally I'll go through it hopefully in 5 minutes or less, and then afterwards we'll go through each point in more detail, in greater depth, and also with additional examples. As the course video gets more difficult, probably by the end of this chapter, I will have review problems for you to try, and then I will also provide solutions for you. I feel obligated to warn you that the biggest mistake students make in linear algebra is they underestimate it. First, the topics. The first topics we talk about are systems of linear equations, and you've been doing these since middle school, but I guarantee you the point is not to review your middle school algebra, but it's really to give you these systems of linear equations. It gives you a concrete kind of example of something to hang on to, so that when we put other ideas and things on top of it and things become more abstract, you have sort of a concrete foundation that you can always go back to and relate to. The other thing about this course that seems deceptively simple is the calculations are very easy. You barely need anything above arithmetic, maybe a tiny bit of algebra, but there's no conic sections, no derivatives, no logarithms, nothing that difficult. But the thing is, the calculations are easy, but what you have to pay attention to are the definitions and the ideas. It's not enough to just sort of vaguely understand the definitions, ideas. You have to be spot on, because that is what this course is about. Don't be fooled by the easy calculations or the middle school looking math. So that's enough advice, at least for now. Now we'll start with the definition of a linear equation with variables x1, x2, up to xn, so n variables. So that's an equation that can be written in the form a1 x1 plus a2 x2 plus an xn equals b, where a1, a2, xn, and b, those are all either real numbers or complex numbers, but they're basically scalars. They're not variables. So what you don't see here is a variable times a variable. It's a variable times a constant plus a variable times a constant, etc. The other thing you don't see is any variable raised to any power other than 0 or 1. So some examples. Here we have 4x1 minus 5x2 plus 2 equals x1. This is an example of a linear equation. We also have x2 equals 2 times 6 to the 1/2 minus x1 plus x3. This is a linear equation. What is not linear is 4x1 minus 5x2 equals x1, x2. This is not linear because you have two variables multiplied by together. The next one, x2 equals 2 x1 to the 1/2 minus 6. In this case, the variable is raised to the 1/2, so this is not linear. Here we had a constant raised to the 1/2. That's okay. And then last we have 2x to the minus 1 plus 6 sine x2 equals 0. This is not linear for two reasons. This x is raised to the minus 1, and also because we have a sine x. Looking at a system of linear equations, we can have m by n systems of linear equation is a system of m linear equations with n unknowns. So for example, 2 by 3, that's two linear equations with three unknowns, x1, x2, x3, x1, here x2 is multiplied by 0, and x3. And to find a solution to this system of linear equations, what we're looking for is an x1, x2, and x3 that solves both the first and the second equation. So x1 equals 5, x2 equals 6.5, and x3 equals 3 will solve both equations, and you can plug them in and see that it is a solution to both equations. Two linear systems are equivalent if they have the same solution set, and we'll be making use of this as we solve systems of linear equations. A system of linear equations can have infinitely many solutions, no solution, or unique solution. So remember, these linear equations, they're sort of in a line kind of form. You don't have any quadratic terms because you don't have a variable times a variable. There's no x squared, there's no xy. So you basically have these lines, which is why they're called linear. And so just looking at two variables, because that's easy to draw, you can have two equations that are essentially just a scalar multiplication. Like if you multiply by 2, you get this other equation. So they're really the same line. So 2 coincidental lines, that will give you infinitely many solutions, right? Every point on this line is a solution both to the first equation and the second equation. So that's infinitely many. You can have no solution. So two parallel lines, there's no point that solves both this equation and that equation. So that's no solution. Or you can have a unique solution. The lines can cross at one single point, and this one point will be the solution to the system of equations. So for linear equations, these are the only three possibilities. There's no such thing as two solutions. It's either infinitely many, no solution, or one unique solution. One thing that'll be really useful is we're going to use matrix notation. So here we take the coefficients and put them in a matrix. So we have 1, minus 2, 1. We have a 0, 2, minus 8, 5, 0, and minus 5. This is our coefficient matrix. We can make an augmented matrix by adding in the solutions 0, 8, and 10. To solve this linear system, we're going to use elementary row operations, and each of these elementary row operations will give us equivalent systems, so we'll still keep the same solution set. So one thing we can do is we can interchange these two rows or these two rows. It won't affect the solution. The second thing we can do is multiply an entire equation by some non-zero scalar. That will not change our solution. And last, we can add a constant multiple of one equation to another. So we might multiply 2 times this equation and add it to this second equation. That resulting equation then can replace, say, maybe the second equation, and we still have the same system of equation. When we solve this, we want to get things in kind of this echelon form, which is this upper triangle, and the lower triangle is zeros, but we'll be working with that and with more examples. That's the 5-minute overview of what we will be covering, and I will now go through each topic again a little slower, a little more detail, and with added examples. We'll back up to the beginning and talk about the definition of a linear equation with variables x1, x2 up to xn. So there's n variables, and they're in an equation that can be written in the form a1 x1 plus a2 x2 plus an xn equals b, where a1, a2 up to an and b are all scalars. They are real or complex numbers. So in other words, what you don't see are two variables multiplied together or a variable multiplied by itself. So you don't have any coefficients of these variables except for possibly 0, x to the 0, or x to the 1. There's no x to the minus 1, x to the 1/2, or x squared. There's none of that. It's just literally variable times constant plus variable times constant plus variable times constant, and then finally you have equals a constant. Here are some examples of linear equations. So we have 4x1 minus 5x2 plus 2 equals x1. And just for emphasis, I rewrote this equation. I brought the x1 over. So I have 4 minus 1 x1. I have my minus 5x2, and then I brought my x2 over to the other side. So I have 3x1 minus 5x2 equals minus 2, which is exactly in this form. Remember, the linear equation can be written in this form. It doesn't mean it presents itself in that form. I did the same for this second example. X2 equals 2 times square root of 6 minus x1 plus x3. So I rewrote that into the form of 2x1 plus 1x2 minus 1x3 equals 2 square root of 6. These examples of equations that are not linear, we have 4x1 minus 5x2 equals x1, x2. So this x1 times x2 is not linear. Here we do not allow for variables to be multiplied by each other. Our next non-linear equation is x2 equals 2 times x1 to the 1/2 minus 6. And this x, the square root of x1, is not linear. Remember, no powers of x except for 0 or 1. And our last example of not linear is 2 to the x1 to the minus 1 plus sine of x2. So 1 over x1 is not linear, and the sine of x2 is also not linear. We don't allow for any fancy functions like sine. Oh, and also one other thing. The square root of x here, the variables cannot be raised to the 1/2. But constants can, because that just gives us another constant. So this is fine here. This is not. Next, we can talk about systems of linear equations, which you have probably solved since middle school. But anyway, an m by n system of linear equations is a system of m linear equations with n unknowns. So here we have a 2 by 3 system of linear equations. The two linear equations, so here's our first equation, here's our second, with three unknowns, x1, x2, x3. x1 here, x2 is multiplied by 0, and x3. So two equations, three unknowns, 2 by 3. So it's also important, the m by n, this is the number of rows, n is the number of columns. M by n, rows and columns, that'll come in handy later. So a solution to this system of equations are ordered triplets, x1, x2, x3, that satisfy both equations. So we can plug in x1 equals 5, x2 equals 6.5, and x3 equals 3 into this first equation, and we get 2 times 5 minus 6.5 plus 1.5 times 3. So that would be 10 minus 6.5, which is 3.5, plus this would be 4.5, that will give us 8. Or we can plug in also that 5 in for x1, there's no x2 term, and then 3 for x3 here, and we get 5 minus 12, that will give us minus 7. So again, this is a solution to our system of equations. We also have this definition: two linear systems are called equivalent if they have the same solution set. For example, if I took this new system of equations, so I copied the first one, 2x1 minus x2 plus 1.5x3 equals 8, and then I multiplied this equation by 2. 2x1 plus 0 minus 8x3 equals minus 14. It will have the same set of solutions as this 2 by 3 up here. So this 2 by 3 and this 2 by 3 are equivalent linear systems because they have the same solution set. This next statement, a system of linear equations can have infinitely many solutions, no solution, or unique solution, is most easily seen when we have two variables, x1 and x2, because then we can draw these lines. But essentially what you want to know is, because these are linear equations, you don't have any kind of curves or quadratics or anything, or cubic functions, because we don't allow for a variable times a variable, and we don't allow for variables to have any exponents other than 0 and 1. So essentially, even in multi-dimensions, these are linear. They're kind of like lines. So when do we have infinitely many solutions? When our two equations are essentially just scalar multiples of another. So when I multiply this equation by 2, it's really the same line. And why do we have infinitely many solutions? It's because every point on this line is a solution to the first equation and a solution to the second equation. When do we have no solution? Well, that's when we have parallel lines. So this is an example here. You can see there's all the points on this line that satisfy this first equation. None of them are in common with the points on this line that satisfy the second equation. Last, we can have unique solution when the lines cross, when they intersect, and that point of intersection, this point here, satisfies both this first line as well as the equation for the second line. And it's easy to see here, and I would keep this in mind. It's really important that you don't go looking for 2 solutions or 3 solutions. That's just not a thing. For linear equations, you're only going to have 3 possibilities: no solution, unique solution, or infinitely many solutions. Next, we're going to use matrices to represent our system of linear equations. So for example, if we have the system x1 minus 2x2 plus x3 equals 0, we're going to take the coefficients 1, minus 2, and 1. When we have our second equation, 0x1, 2x2 minus 8x3, we're going to take the coefficients 0, 2, and minus 8 as our second row. And for our last equation, if we have 5x1 plus 0x2 minus 5x3, we'll take the coefficients 5, 0, and minus 5 as our third row. We can make an augmented matrix here by putting the solutions 0, 8, and 10 on the other side. And this will help us when we're solving systems of linear equations, because we don't have to keep carrying around the variables, it'll be really handy. You'll see that in a minute. But even more importantly, as we go on in class, this will have other significances as well. And just to remind you then, this first column, these are the coefficients of x1. The second column is the coefficients of your second variable. And this last column are the coefficients, right? This third column is the coefficients of your x3 variables. So it's also useful to remember these columns correspond with these coefficients. Finally, in this video, we're going to look at solving linear systems, and we're going to do that by using these row operations to make equivalent linear systems that are easier to solve. In our next video, we'll look at how to be super efficient at solving these. Here is my example. I'm going to use this system of equations, this 3 by 3. So x1 minus 2x2 plus x3 equals 0. 0x1 plus 2x2 minus 8x3 equals 8. And 5x1 plus 0x2 minus 5x3 equals 10. And these are the three row operations. We can do these, and we will still preserve the solution. In other words, the new system of equations we get by doing any one of these or any number of these will give us an equivalent system, a system that's equivalent to our original equations up here. First, I'm going to do number 1, the interchange of two equations. Here is my original system of equations. And then what I'm going to do is interchange these two rows. So I'm going to bring the second equation up at the top, 2x2 minus 8x3 equals 8. And then this first equation is going to be the second equation, x1 minus 2x2 plus x3 equals 0, 5x1 minus 5x3 equals 10. I also wrote this with our matrix form, and you'll see that it makes it much cleaner. So my coefficients will be 1, negative 2, 1, 0. 0, 2, minus 8, 8, and 5, 0, negative 5, 10. And then my ending equation is or matrix will be 0, 2, minus 8, 8, 1, minus 2, 1, 0, and 5, 0, minus 5, 10. And what I do is I often say to get from this matrix to this, I put an arrow, and I say what I'm doing. So when I swap rows, I have R1, and I have the back and forth arrow R2. This is for me telling me I'm swapping row 1 and R2. And I'm going to use this notation all the time. Your book doesn't have it, but I really like it. You'll see it. I'll show you how I do the notations for these other two row equations or row operations. The next row operation is to multiply an equation by a non-zero scalar. So what I did here, this is again my original set of linear equations. And now what I did to get my new set of linear equations here is multiply this second line by 1/2. So I have my first equation, my third equation are untouched. I have 1/2, so that'll give me x2 minus 4x3 and then equals 4. So my matrix representation, again, I have the same starting matrix, and then I designate that what I'm doing is multiplying R2 by 1/2, and then here's my resulting matrix. And I'm just going to check to make sure I have it right. That would be 0, 1, minus 4, and 4 in the top row, and the bottom row are the same. The last row operator is to add a constant multiple of one equation to another. So here what I did, I added these two equations here, and I replaced the second equation with this addition. So my first and third row are the same, and my second equation then is replaced with R1, the first row, plus the second row. So here we're going to have x1, actually I missed my x1, should be here, plus 0x2, because I have these two cancel out, and then I'll have my minus 7x3 is equal to 8. So here I should have, this is my original equation here, and over here I should have a 1. Yep, a 1. And the way I notate what's happened is I say that I've replaced R2. So this first, it's significant that I put R2 in front of R1 because this is the row that I'm replacing in my matrix. And I'm replacing it with R2 plus R1. So here I add I get 1, 0, minus 7, and 8. And the claim is that these row operations, so these new systems of equations that we have here on the right-hand side, have the same solution set as our original equations. So the two systems are equivalent. So the idea is we want to use these row operations to change our matrix into something that looks like this upper triangular. And by upper triangular, I mean that if you draw the diagonal along your matrix of coefficients, then you will have zeros underneath the diagonal, and above the diagonal you can have zeros or numbers. So we'll do examples of that. Our first example is to solve the system of equations x1 minus 2x2 plus x3 equals 0, 2x2 minus 8x3 equals 8, and 5x1 minus 5x3 equals 10. And I wrote our elementary row operations here that'll allow us to get equivalent systems of linear equations. And the first thing I do, I've written my coefficient matrix, but I am going to be working with my augmented matrix here. So the coefficients are 1, negative 2, 1, 0, 1, negative 2, 1, 0, 0, 2, negative 8, 8, 0, 2, negative 8, 8, and 5, 0, negative 5, 10, 5, 0, negative 5, 10. Remember, the goal is to get this upper triangular form, and we want to do this in a systematic way so that we're going to start by, well, the first row, first column can be a number, which is what we have, so that's good. We're going to start by trying to zero out the first column. And we're doing this in a systematic way because if we don't zero out the first column and then we add it to something else, we'll just kind of keep getting numbers popping back in. But like once we zero out the first column, then we're good to work on zeroing out the second column. So I recopied my matrix here, 1, minus 2, 1, 0, 0, 2, minus 8, 8, 5, 0, minus 5, 10, and I want, here's a 0 here, which is good, but I also need to get rid of this 5. I want to make this a 0. So what I'm going to do is add minus 5 times my first row to my last row. So I'm going to note that R3 minus 5R1, and remember R3 because that's the row we're replacing, and we're going to add minus 5R1 to R3. That'll be our new R3. So minus 5 plus 5 is 0. Minus 5, that will give us 10, plus 0 is 10. Minus 5 here, plus minus 5 will give us a minus 10. Minus 5 times 0 is 0, and then we'll get a 10. And just to see where I'm at now, I went ahead and drew my diagonal, and I drew my staircase. So what I need is, to get this to be 0, I'm going to multiply minus 5 times R2 and add it to R3. Obviously, well, I wouldn't want to multiply the first row by 5 because that would make a 5 pop up here. But because this now has a 0, I can do this with the second row. So I'm going to replace R3 with R3 minus 5 R2. So 5 minus 5 R2, minus 5 times 2 would be negative 10, so this gives us our 0. Minus 5 times 8 would give us positive 40, plus negative 10 would give us 30, and then our minus 5 would give us minus 40, plus 10 is minus 30. So this is our second row, and we're in upper echelon form now. I can draw my staircase, and everything underneath the diagonal now is equal to 0. The other thing I did, just to make things easier for myself, is I multiplied the second equation by 1/2, and I multiplied this bottom equation by 1/30 of R3, just so I can have some smaller numbers to work with. I've written my variables here to remind me that this first column are the coefficients of x1, the second column are coefficients of x2, and this third column are coefficients of x3, and this last column is my b, my solution vector. My new set of equations then become x1 minus x2 plus x3 equals 0, 0x1 plus x2 minus x4 equals 4, and finally x3 equals negative 1. So I have x3 equals negative 1, and now I can plug x3 equals negative 1 into here and solve for x2, and then once I solve for x2 and 3, I can then plug x2 and 3 in here and solve for x1. So here I've solved for x2, I've solved for x1, and I find that 1, 0, minus 1 is a solution to the system of equations. Also, when I plugged x3 into this equation to solve for x2 and then plug x2 and x3 to solve for x1, that's called back solving. If you don't like to back solve, you can kind of row reduce this even further. The reason why you have back solving is because you have this this 4 here and the 2 and 1 here. So what we can do is do one more row operation. So I started with 1, negative 2, 1, 0, 0, 1, minus 4, 4, 0, 0, 1, minus 1. I can do this one more row operation, which is to replace R2 with R2 plus 4 times R3. So here we have 4, this would just give me 1. 4 times R3 would give me 0 here. 4 times R3 would give me negative 4, so I'd have a 0. So this makes it a little bit easier. I have x3 now equal to 1, x2 equal to 0, and then I still have this last one, x1 minus 2x2 plus x3 equals 0, so I do have to still do some back solving, and I get the same solution, 1, 0, and minus 1. And this solution is in fact a unique or the unique solution. I'll show you what it looks like when you have infinitely many solutions or no solutions later, but there is one solution and it is the unique solution. Also, when there is a solution, so either infinitely or unique, we say that the system of equations is consistent. So I believe your book has the same system of equations, and the question was determine if the system in the previous example is consistent, and the answer is, well, yes, since there's a solution, the system is consistent. Again, consistent just means it has a solution. It could be a solution or infinitely many. Here is an example of a set of equations that is inconsistent. In other words, it has no solution. Let's walk through this one. I start with my augmented matrix, so I have 0, 1, minus 4, 8, 0, 1, minus 4, 8, 2, minus 3, 2, 1, 2, minus 3, 2, 1, and 4, minus 8, 12, and 1. 4, minus 8, 12, and 1. Looking at my form over here, I can leave this 0 here, but if I just swap the position of these two, I have one less calculation to make this first row have zeros underneath the diagonal. So that is exactly what I do. So I notate the swap. I'm swapping R1 and R2, row 1 and row 2. And now the next step then is I want to make the first column this all zeros except for this first number, right? So it looks like this. The first number can be a number or a 0. Everything underneath needs to be 0. So now my second step is to replace R3, because I want a 0 here, with R3 minus 2R1. So multiplying minus 2 by R1, I get minus 4 plus R3 is 0. Minus 2, that would give me 6, plus minus 8 would give me minus 2. And now I have a minus 2, so this is minus 4 plus 12 will give me 8. And now I have a minus 2 plus 1 will give me minus 1. Looking at my diagonal, now I just need one more 0 here. So what I'm going to do is replace R3 with R3 plus 2R2. So multiplying by 2, I'm going to get 0. Multiplying by 2, I get minus 8, so I'll get 0. Multiplying by 2, I get 16 minus 1 will give me 15. I write my x1 under this column because these are the coefficients associated with x1, x2 under this column, and x3 under this column. So what I get is 2x1 minus 3x2 plus 2x3 equals 1. And I wrote that equation here. I also have 2x2 minus 4x3 equals 8. I wrote that last equation. And then here I'm going to get 0x3, which is equal to 0, equals 15. So this is what makes it inconsistent. It's not consistent because there's no x3 that can satisfy 0 times x3 equals 15. So this is what it looks like when your system of equation has no solution. We've done an example of a system of equations that had a unique solution, and now we just did an example of a system that has no solution. So I wanted to show you an example of a system with many solutions. For our example of a system of equations with infinitely many solutions, we have this 3 by 3, 3 equations, 3 unknowns. The first equation is x1 minus 2x2 minus x3 equals minus 2. The second equation is 2x1 plus x2 plus 3x3 equals 1. And the third equation is minus 3x1 plus x2 minus 2x3 equals 1. And here is the augmented matrix to represent this system. The first row is 1, negative 2, negative 1, negative 2. The second row is 2, 1, 3, 1. And the last row is negative 3, 1, minus 2, 1. And looking at this, remember, this 1 is fine, but we want the rest of the row, the column, sorry, to be 0. So we need a 0 here in this 2 position and a 0 in the minus 3 position. So I did 2 row operations to get this matrix. The first one is I replaced R2, the second row, with R2 minus 2R1. So I multiply R1 by 2, or minus 2. When I add these, I'll get 0. Multiplied by minus 2, that will give me positive 4, plus 1 will give me 5. Multiplied by minus 2, that will give me positive 2, plus 3 will give me 5. And then multiply by minus 2, I'll get 4, plus 1 is 5. On the bottom, I replace R3 with R3 plus 3R1. And then again, that gives me a 0 in this position. And then 3, that will give me minus 6 plus 1 is minus 5. 3 would give me minus 3, minus 2 is minus 5, and minus 2 times minus 2 times 3 will give me minus 6 plus 1 is minus 5. So the next thing I need to do is get a 5 in this position here. And that will give me that form where I have everything under this diagonal equal to 0. So I can do that by replacing R3 with R3 plus R2. Fortunately, I can just add them together and I'll get 0, 0, 0, 0, which is very nice. And then one other simplification is I wanted just to make this into smaller numbers, so when I back solve, I have small numbers. So I divide R2 by 1/5 and I get 0, 1, 1, 1. Now I label my columns with x1, x2, x3. So reading from top to bottom, I like this because I can get the easy ones first. Like this is a more complicated equation. So what I get is 0x3 equals 0. So far we have no restrictions on x3 because any number you want to plug in for x3 will work here. Then we have x2 plus x3 equals 1. In other words, x2 is equal to 1 minus x3. And then x1 minus 2x2 minus x3 equals minus 2. So x1 is equal to minus 2 plus 2x2 plus x3. Now I'm going to plug this in, my x2 equals 1 minus x3 for x2 here. So I have my minus 2, 2 times 1 minus x3 plus x3. So what that will give me, these cancel out, that'll give me minus x3. So what we have is x3 has no restrictions. It's what we call a free parameter. Then x2 and x1 are parameterized by x3. In other words, once we choose a value for x3, we can solve x1 and x2. For example, if we let x3 equals 1, then we'll have x2 equals 0 and x1 is equal to negative 1. We can plug those into these 3 equations. I chose small numbers, so you should give it a try, and you'll see that it'll solve the system of equations. It's always good just to plug in some numbers and make sure you have a sanity check on your solution. Let's say x3 equals 0, an even smaller number, then what that will mean is x2 is equal to 1 and x1 is equal to 0, so I can plug those in here and I see it still solves the system of equations. So for every choice of x3, there's going to be a solution, and since there are infinitely many ways of choosing x3, there are going to be infinitely many solutions. So now we've seen examples of a unique solution, infinitely many solution, and no solution, and there's no other possibilities. To review what we have covered in this video, first we started with the definition of a linear equation with n variables, x1 up to xn. So a linear equation is one that can be written in the form a constant times x1 plus potentially a different constant times x2 plus an nth constant times xn, and that's also equal to a constant. So again, our a1, a2, an, and b are all constant coefficients. They're either real or complex numbers. And we had some examples here of linear equations and equations that are not linear. And as we said, for not linear, we cannot have variables multiplied by each other, or these variables, their exponents need to be 0 or 1, and we certainly don't have any fancy functions like sine of our variables. We can have sine of the constants, like sine of a would be fine. We talked about systems of linear equations. That's when we have m equations with n unknowns, and we said a solution is a set of the variables x1, x2, x3 in this example that will solve both equations, that satisfies both equations. And then two linear systems are called equivalent if they have the same solution set. And these row operations, I'm going to jump ahead, will preserve our solution set. So when we do these row operations, we'll still have equivalent systems of equations. And the row operations are you can interchange two equations. In other words, you can change the order of the two equations. That won't affect the solution. You can multiply one of the equations by a non-zero scalar. So if you multiplied like the second equation by 2, for example, it won't change the solution to the system of equations. And last, you can add a constant multiple of one equation to another. So if you multiply by 2 and then add with this top equation, you can replace this bottom equation with 2 times the bottom equation plus the first equation. That will not change the solution either. We talked about then solutions of these linear equations. And it's easiest to see when we only have 2 variables, in which case everything's a line. And you can also see the linear form of our equation. That precludes having some kind of quadratic, some sort of curve. So what you're either going to have is infinitely many solutions. That's when your 2 equations really represent the same line. So every point on this line is a solution to both equations. You can have 2 parallel lines, and then there will be no solutions because none of the solutions, points on this line will ever intersect points on this line. Or you can have a single point of intersection that's a unique solution which will satisfy both equations. We use this matrix notation where we take the coefficients to make a matrix, and then also we can add the augmented matrix where we take this solution set over here. And from there, we solved systems of linear equations using these elementary row operations. And our goal was to get things in this upper echelon form where we draw the diagonal going from 1, 1, 2, 2, 3, 3, and then 4, 4. Everything below this diagonal needed to be equal to 0. And that was the way that we learned to solve the systems of equation. So that's it for this video. Thank you for watching.